do work for Grant County PUD, if you guys hadn't got that from some of the email exchange. So we're very excited to have you guys. I've got a whole bunch of people who are going to help with tours and whatnot. I'm a mechanical engineer by degree. I do maintenance engineering here, which means that I get to do about this much engineering and that much everything else. But feel free to ask your questions, reach out, send emails, converse on Slack. I understand that this problem is very heavily mechanically engineering based. So I apologize for those of you who aren't mechanical engineers, but know that we're here to support you. And I'm really excited because I think that those who don't have an engineering background may provide the most unique and out of the box, and may even be able to provide that solution that we're looking for. So great to have you guys.
Libby.
Hi, I'm Libby Poyer. I'm from Wenatchee Valley College, and I'm really excited to be doing this today and for the event as well.
Glad to have you. Dana.
Hi, I'm Dana. I'm from Clackamas Community College. I'm in the Renewable Energies program, set to graduate soon, and I'm very much not an engineer, so we'll go with that.
We're very glad you're here. Okay, Harrison.
Glad to be here.
I'm Harrison Russell. I'm from Clackamas Community College. I'm not an engineer. I'm also doing the Renewable Energies and Technologies program and also working on getting my welding certification. And I'm just excited to be here and meet everybody. And thank you again for this opportunity.
Awesome. Thanks for being here. Sam. And do you like Sam or Samuel?
Sam works. I'm at Tacoma Community College right now. In the fall, I'll be at USC for mechanical engineering. And yeah, excited to solve the issue.
You have a fan already. Shannon's like giving you the big thumbs up.
Awesome.
All right. Jessica, you just put yourself on camera, so you're next.
I'm Jessica. I'm here in Vancouver, attending WCV, and I'm just in electrical engineering. So I'm kind of out of my element, but I'm excited to be here.
You're trying new things. It's great. Skylar.
Good morning, all. Skylar Street. I'm a mechanical engineer with Grant County PUD, or reliability engineer is my title now. I'm a full-time remote employee that lives out in Kentucky, right across the Ohio River from Cincinnati. But I work for Grant PUD full-time, 10 years there on site, 5 years in the plants, and 5 years doing capital projects. So that's my background, and I'll give a little rundown on what Grant PUD is and does, and how we move energy and power across the county.
Well, thanks for being here, Skylar. We look forward to learning more from you. Alvaro.
Good morning, everyone. Good on you. There we go. Hey. So, hi, my name's Alvaro. I'm a student from WVC, trying to get my bachelor's in engineering as well. I have a small background in controls projects at my food processing job, so got a little bit there. But I'm excited to see all you guys here and see what we can do.
Cool. Thanks for being here. Brian.
Hello, can you guys hear me okay?
We can.
Nice,
Sure.
nice. All right, just making sure. But yeah, I'm Brian. I'm from the University of Washington studying mechanical engineering. And yeah, I think it's really cool that not everybody here is doing engineering. You know, I like being on like diverse teams like that, which, you know, I'm excited to see how this whole thing goes.
Cool. Thanks for being here. Joshua.
You're on mute, Josh. Josh, you're on mute.
Does it not come off mute? Okay, we'll move on to someone else for the moment. Aaron.
All right. Yeah, so hello everyone. Yeah, so I'm Aaron. I currently just graduated from Wenatchee Valley College with my associates, and I'll be starting my junior year at UW Bothell in electrical engineering. And I'm also excited to meet everyone. And actually, I know some familiar faces here. But yeah, I'm excited to work with people and you know see what we can do.
Awesome. I wondered if some of you might know each other. That's awesome. Is Luis on yet? Don't see.
I think he just came on.
See? Oh, see, that's what you get for being late, Luis. You have to go right into introducing yourself. Welcome. Maybe his audio is still not. Luis, can you hear us? Would you mind introducing yourself real quick? If we can't hear you. Circle back. We'll give you a minute to get acclimated here. Is Tapiwa here? I don't know if I said that right. Tapiwa? No. And Olga?
Hello.
Hello. There's Luis.
Oh, you guys can hear me now.
Now we can hear you.
One sec. I'm having some technical difficulties this morning.
That's okay.
Hi. My name is Luis. I don't really know what to say about myself. Is there any things you recommend I say?
Just your name and what school you're going to, maybe what your degree is in.
So my name is Luis Alvarez. I go to Wenatchee Valley College, and degree I'm hoping to get in biochemistry.
Awesome. Thanks. Well, thanks for being here.
Yeah, thanks for having
Olga.
me.
Hi, everybody. My first name is Olga, but I go by Pauline, my middle name. So hi, I'm Pauline. I also attended Wenatchee Valley College, got my AA, but I'm going to continue going there for the convenience, and then I'll have to decide on what I want to do because I'm interested in a lot of things. But either environmental engineering or physics are what I'm interested in today.
I love it. Well, thanks for being here. Pauline, I wondered because I saw both names and I was like, uh-oh, which one does she go by? So I'll make a note of that. All right. And I don't see Shaka on yet, but that would be another student. And so we can circle back to the last two that I don't see on yet. Chad.
All right, good morning, and I guess good afternoon to Skylar, huh? Back east. It's Chad Croft. I'm with HDR, a civil engineer by trade. Haven't really done any engineering for probably 15 plus years. Part of that is because my previous job to HDR was with Portland General Electric. I did do some engineering there, but the last 14 years that I was at PGE, I was on site at a hydroelectric facility here in Central Oregon. I'm based out of HDR's Bend, Oregon office. I've been with HDR for about a year and a half, and I was with Portland General Electric for 19 years. And Bree, you said Chris could introduce what college he's attending, but am I not looking young enough with my receding hairline and gray hair that I can't introduce my college?
It was definitely not judging that.
Okay.
But you do have a daughter that's married, and I knew that already. So
yeah, thanks for pointing that out and making me feel even older.
All right. And Bill.
Yeah, I'm Bill Brown. I am mechanical and nuclear engineering by degree. I work at the Grand Coulee Hydroelectric Dam up in Washington. I run the design and planning engineering group here, so I supervise a team of mechanical and electrical engineers. And I too am old like Chad, so old enough to be all y'all's father, but that's okay.
I prefer wise.
Wise, okay, yeah. The gray hair and
Wise.
beard makes
Not
us
old.
wise, yeah.
I see Ashley's on now. Ashley, can you introduce yourself real quick?
Yes, I'm Ashley Beck. I am studying construction engineering management at Oregon State University. I am so excited to learn more about hydropower projects and make some new friends.
Awesome. Glad to have you. All right. And Steve.
Me, Steve?
You, Steve. You're the only Steve.
Sorry about that. So my name is Steve Winke, and currently president of the Hydropower Foundation. So I'd like to welcome everybody, and we're glad to have you come and participate with this. You will, I know, have a fantastic experience. Bree and everybody put on a great program for you. So get ready to learn and see a lot of things, and hopefully with that you will come away with a lot of excitement toward the hydropower industry, and maybe we'll see you in there someday. So my personal background, I retired. I worked for a utility for about 40 years, and so I retired recently. So in terms of age, I go back to when the ice sheet still covered the North American continent. That's about the time I started working, so it's been a while. But anyway, I do want to welcome everybody and look forward to this. So thank you.
Thanks, Steve. I think I got everybody, but please raise your hand if I missed you. Chris, you were not missed. You were like the second person. Don't mess with me.
I didn't say anything. I haven't said anything. All right, so I'm Chris Eden. I'm a student at Boston University. I'm 22 years old. Is anybody buying that? Okay. No, I am an electrical engineer at Stantec. I've been in the industry for 15 years doing consulting design. Started at Stantec and have continued there. So I've only done consulting design. But one of the things that I think is interesting about this industry and all the people that you've talked to, we've all either worked together through our businesses have shared. I've done work for Grant County PUD. I've done work for the Bureau of Reclamation. I've worked with HDR. We're all interconnected in this industry, and we all kind of have a lot of shared experiences. And we're all really excited about what we do, and we're happy to share it with you, and hopefully get you guys excited and get you interested and pull you in to this to the industry that we love so much. So we're looking forward to this experience, and I can't wait to see what your interest is.
Thanks, Chris. Sorry. Okay, so I'm going to jump into just a few of the housekeeping items to give you a little bit of an idea on what to expect as you arrive to the think tank competition. You're going to need to check into your hotel. We are staying in Ephrata at the Best Western Rama Inn. And all of your names are already on the list. They already know you're coming. So all you need to do is check in and provide a credit card for just your incidentals. So the foundation will cover your lodging. And breakfast will be served every morning at 7:30. That's when we will be meeting. So first time you'll see us will be Tuesday morning at 7:30. Hopefully I'll have a cup of coffee in my hand, so I'm bright-eyed and bushy-tailed. But so that's kind of like as you arrive, you're going to need to make sure you eat on your own that evening, that Monday evening. And then we'll all meet up for breakfast at 7:30 on Tuesday, the 16th. Let's see. Wanted to make sure that everybody got on the Slack channel. If you have not, for some reason, please let me know and I'll try to invite you again to make sure that you're on there, because we're sharing a lot of documents on the Slack channel and want to make sure everybody's able to access that. Okay, Josh, your mic is working now, so you can introduce yourself.
Okay, you guys can hear me?
Yep.
Okay, sweet. My name is Josh, and I do renewable energies technologies at Clackamas Community College, and I have a little tiny bit of a background in physics at the college from years ago, and live down in Oregon, just south of Portland, and looking forward to seeing you guys. And sorry for the late entry there.
No worries, no worries. Well, thanks. I'm glad you're here, and I'm glad your mic is working. So if you have questions along the way, definitely let us know. I don't know if you guys gathered this, but I'm not an engineer either. So you're going to have to direct all of your engineering questions to Shannon and Chris and all of the other really smarty pants in the group. I am a communications major. I am all about, having fun and visiting with people and building rapport. So happy to get to know you guys and learn what you want out of a career. And I would love to help connect you to the right people. So that's what I'm good for. And getting you to Washington. Hopefully I can get you to Washington.
I don't promise my answers to be smart. I want to clarify that right off the I will do my best, but no promises.
All right, cool. So yeah, so Slack channel, make sure that you're on it so that you can have all the documents that we've been sending. Also, there are still a handful of you that need to send me your lunch orders. I need to send those in today. She wanted a 2-week lead. So if you haven't yet sent me your lunch order, don't make me guess. I don't like guessing for people. I don't know what people like. So send me your lunch order if you can today. Again, so this is today is your opportunity to hopefully answer some questions that you guys might have. I'm hoping that some of you all have met virtually, talked via email, had thrown out some ideas at this point. So Shannon's going to go over more of the problem and really give you some insight into what you're going to need to do and kind of the history of what's already been done to try to give you some insight, because we want to make sure that you have as much information as you can to make an educated solution out of it. So Shannon's going to do that along with Chris. I think Chris is going to jump in and help her here and there. And then Skylar's going to give you kind of a Hydro 101. Some of you might know a lot about hydro and some of you might know very little. So we're going to come at an angle of assuming you know nothing and just start there. That way we make sure everybody's starting at the same level. Any questions thus far? Okay,
Real quick,
well then with that, I'm turning it over to Shannon.
So I will say with the lunch order that Bree told you guys about, if none of those look good, you're going to want to plan on bringing your own lunch, because for the most part, day 1 and day 2, we are going to be at the Hob, which is the hydro office building down in front of Wanapum Dam. And the closest lunch options are a minimum of a 15-minute drive away in a town called Mattawa. There's a Subway, some Mexican restaurants, a gas station that sells burgers, and they're not half bad, and a grocery store. But we don't have the ability for you day 1 and day 2, if you don't like what's being offered, to walk across the street and grab something to go. To most of us who work in hydropower, that's the beauty of working in hydropower, is these beautiful locations we get to work at. One of the frustrations is that going out to eat is not really an option. Today, we found out we're going to have a food truck in the parking lot of the Hob tomorrow. And let me tell you, that is like, yeah, we're buzzing around here. Everybody's like, you go in, you go in. So if you haven't got those lunch orders in, this is my 2 cents on why you definitely want to get your lunch orders in. In addition to that, I was going to let Chris lead going over the problem statement and kind of just chime in on questions. But I will also say that Skylar is quite the expert on fish ladders. And while we have him here, please ask any and all questions, because if I don't know the answer, I will fully admit he's going to be the first person I call. And maybe he would be so kind as well as to leave his email address, and you guys can reach out to both of us if you have some questions too. He is absolutely probably one of the most brilliant engineers I know. So Chris, did you want to take it away with the problem statement and I'll chime in?
Yes. Give me 1 sec while I get it pulled up.
Perfect.
Hold on 1 sec.
I'll just add my 2 cents real quick on lunch. The reason we coordinate lunch beyond the fact that we want, to feed you, but it's also because we have your whole day planned. So we've got a lot of things going on. We've got sessions that we're giving you and doing tours and whatnot. And so we really try to schedule lunch so that we can all eat at the same time and get moving to the next thing. So that's all I wanted to say about that.
Yeah, lunch at the last competition was a great time for teams to get together and work. It was a great time to ask your questions. It was a great time to mingle with industry experts. So eating with us, which don't get me wrong, if you need a mental break, we have a beautiful turbine park right on the river, right in front of the Hob. If you want to take your lunch and just get away from the chaos, you're welcome to do that. But lunches and dinners have been a great way to network and talk.
Okay, so I'm guessing that each of you had a chance to kind of read through the problem statement. And one of I think the key things that we tried to focus on when developing the problem statement is we wanted to find a project that would give you, kind of a varied opportunity to look at some different skill sets, things that would be, that are going to have challenges from a construction perspective, challenges from an operations perspective, challenges from an electrical perspective, challenges from a mechanical perspective, and all sorts of different aspects to this project that we typically come across in our engineering projects on a daily basis. So the problem statement is going to be the auxiliary water system at the Wanapum Dam. It is the valves that are located. Thanks, Shannon. So if you read all this, kind of the background of the Wanapum Dam, which, by the way, I think I'm correct in saying this was a Harza design, which is technically the company that my company was before the company that it was this company. But anyways, that's a whole nother story that I can tell you about. So we've gotten purchased and sold and all sorts of stuff multiple times. But Legacy, this was the project that one of the projects that the Legacy that I come from built. So on the auxiliary water supply system, there's a couple of valves, butterfly valves that are down in this very deep chamber. Located, there's two valves. One's typically used for isolation and one's control, right, Shannon? I got that right?
Yeah, we call it guard and the guard valve and the regulating valve. And I will input right here. The valves are an indication of the system, but we're not focusing on the valves themselves. We're focusing on the entire attraction water supply.
Correct. So what they're looking for is this is a very old system, and they've had some issues with leakage and some other maintenance issues, and so we're looking generally for improvements to the system where opportunities to improve the system, repeat the function, and maintain the functionality of the system. One of the key things I think that is important to this is when we do engineering design is coming up with concepts. A big thing is not just how do we solve the problem today, it's how do we solve the problem in the future, right? What we're going to install, how is it going to be maintained? How is it going to be operated? How is it going to be, what benefits does it provide to the client in the future? There's all sorts of questions that we ask ourselves when we start an engineering design. But the most important thing that you got to start on and focus on is what is the function and what are the goals that have been presented from the client, right? And so as you read through the problem statement, I think Shannon did a great job of writing up a lot of kind of what the purpose of the system is, what the function of the system is, and what we're trying to maintain in improvements to the system. And so that's what you need to focus on. A big part of it, I guess the way I look at this, there is a lot of ways to approach this, right? And no single way is wrong. Okay, there isn't a right answer to this problem. Okay, when you approach this problem, we want to see unique ideas. We want to see creativity. We want to see, that you've thought through this and that you're really looking at opportunities, even if they're kind of outlandish. We're okay with you presenting that. We're interested to have you think outside the box. Engineering, a lot of times there are 1,000 ways to answer a problem, and you have to kind of, sort through all of those options and then pick one and move forward with it, right? That you think is, in your judgment, is the best option. So when I approach a project like this, the way that I start is I start with, what is the client asking for? What are their goals? And then what are the key aspects to the system that I could adjust to meet those future goals? What component of the system, and focus down on that. And again, there may be a variety of different goals here, right? And you can't necessarily answer all of them, right? I mean, so I guess in my view, and Shannon can chime in with what her feeling is on this, but my view is, pick an aspect of this, or pick a some component of this that you want to improve or you think you can make better, and kind of focus in on that. Because then if you take on too much, you're going to spread yourself too thin, and you're just going to be, churning your wheels, right? So, my key thing with engineering is, try to focus, try to cut the problem into manageable chunks, and then manage those individual chunks. That's how I always approach a project. Because sometimes if you look at it from the big picture, there's just too much. So I think focus in on something that you feel comfortable with. If you want to just throw something out there, throw some spaghetti, see if it hits the wall and sticks, go for it. However, we are going to scrutinize the viability. We'll kind of look at it, and I think if it's completely outlandish, we want you to have thought through how to apply it. But we're happy to see that. But on the other hand, we're also looking for something that works. So it's kind of a balance between the two. So I don't know, Shannon, if you want to get into anything more specific than that. I mean, that's kind of the approach I would take to the problem set. I think everybody's read through this, so I didn't want to dive too deep unless there's something specific you want to talk about in providing that approach. And again, the other thing I do suggest, reach out to us. I mean, we're going to be resources. I'm happy to kind of answer questions. If you're banging your head against the wall on something and you just have a quick question, part of what my job is understanding my boundaries, understanding my own limits, and saying, okay, well, do I know somebody who knows this better than I do? And can I reach out to them to, give me an idea or spark a thought or something like that? It's one of the things that I do. I'm constantly talking to my civil engineers, my structural engineers, my mechanical engineers. I'm talking to the environmental group. I'm talking to, anybody in any other group to help me, fill all the gaps that an engineering project kind of brings to the table.
No, I think all of that was great, Chris. I'm going to walk a little bit through the attraction water supply here in just a sec. But what I definitely want to focus on, as Chris said, we're really looking for solutions. And when I was researching this attraction water supply so that I knew enough that I could write a problem statement about it, we created an attraction water supply down at Priest Rapids that hadn't been there before. And Skylar was kind enough to say, oh yeah, we have documents of we hired Jacobs Engineering to come in and create a solution for that. And Skylar was actually in on that project. But what struck me when I read the paper, because they're really great about creating these documents, was it was a team of PUD engineers and Jacob engineers sitting around a table, and they legitimately threw out ideas. And maybe it wasn't on the attraction water supply, it was on uh, methods for mitigating for milfoil, which is an issue here too. But it was so fun to read because it really was a spaghetti approach. They threw out like maybe we can burn the weeds, or maybe we can divert flow, or the ideas that they threw out there to kind of just let everybody stew on were so varied. They were really complicated and needed some really big studies, to really expensive, too cheap, and not complicated at all, but maybe might not work. So even if you guys can get together as a group and just start throwing out ideas, even if each group ends up duplicating a solution, the way you guys are going to approach it and the way you guys can justify it are probably going to be vastly different. So it may be worth for all of you guys to get together and talk it through and share that knowledge. Then each group decide on what solution they think is going to fit this best, take it back to their team, and the team start working on a justification. I will say day one, we are going to go and visit this space. That is, we're going to drive you down to the hub. We're going to gear you up with safety equipment, and we're going to take you over so you guys can see this area and get a feel for what we're asking you to do. So that would also be part of my recommendation for getting together as one big group and throwing out some ideas, and maybe not going too far down a solution path with any one of them, because once you see the space, it may negate whatever you thought the answer could be. You had something to say, Chris?
Oh, I wanted to, milfoil is a plant, I'm assuming.
It is.
Okay.
Yes. Yes.
Yeah, okay. So I want to pair with that though a little bit, and one of the key things that we always start every engineering project with is a site visit. Particularly when you're a project like this, where it's a rehabilitation project, you are working within a given space. I mean, just so you understand, we're not going to tear the dam down to make your thing work, okay? So you have to work within the footprint that we're given. And it's one of the challenges that I find makes this job so much fun, but also incredibly frustrating at times, because when these dams were built in the 50s and the 60s, or even one that I just finished, which was from 1912, they did not consider modern codes and requirements and spacing and all the other things when they were building these things, and it presents challenges that you're not going to get in other industries. If you're doing a new building from the ground up, you get to build the space around the stuff that you need. Here we have to make the stuff fit, and which sometimes works and sometimes creates really creative solutions that we have to come up with. Steve, you want to chime in?
Well, I would just like to point out in the nature of brainstorming that we're discussing here, but just because we're not going to tear the dam down doesn't mean necessarily the dam can't be modified, possibly, right? So just don't start closing doors, Chris, before they get started. That's all I was getting to.
Fair point. Fair point.
I was actually going to mention the same thing, although if you're going to talk about modifying the dam and cutting concrete and doing that, we're going to want a really
good reason.
a guess, a reason, a guess, give us some numbers to justify. Like, we want justification. I can't say anybody's going to really look into your numbers or maybe be able to contradict whatever that guess is. But we want to see that you've thought about some of that stuff. So if you think it's going to cost $1 million to cut in the dam, put that in there and sell it to us, kind of deal. But
Also, I want to know the
justify
contractor
it.
to that price.
But justification, that's the big word I want you to take away from today. Whatever your solution is, give us a good justification. Sell your justification and use everything within your resources to sell it to us. Skylar, you had a comment.
I was going to interject that we do cut concrete fairly frequently around the dam. The right bank project we did at Priest Rapids, we cut multiple holes in the dam. You have to build boxes to keep the water out of the holes that you're cutting, and that's a significant load. Those boxes turn into balloons, or helium balloons. They like to float when you fill them full of water or full of air and not water. So yeah, it's all stuff that we get to figure out and work through and sharpen our pencils for.
Yeah, as an electrical engineer, I've been yelled at multiple times by the structurals for cutting their rebar. So, you can do it. You got to make sure that you get everybody's buy-in, though. It's real important, or else you're going to get yelled at.
That is true. So I'm gonna go back to the problem statement. I'm gonna walk you guys through because I know I don't want to bombard you guys with too much. And what Skylar's presentation on the Hydro 101 is great. So I definitely want to make sure we have time for him and any questions you guys might have. Real quick, so the reason I brought up this picture is this is a picture looking at Wanapum Dam. What you have here is the river flows from the top left corner down to the bottom right corner, and you can kind of see that with the turbulence that you can see here. What we're looking at right here with all these pier noses is our spillway. And back here in this back picture, you can see our powerhouse, and that's where we house our 10 generators. And all of this you guys will get to see when you make it here. But what I really want to focus on is the right bank fish ladder. And this is where our problem is focused at. And so that's why I included this picture, and I love this picture so much, is the attraction water supply that we're focusing on is underneath this right bank fish ladder. And this whole structure here is part of the right bank fish ladder. You can see part of the attraction water supply down here, and you can kind of see water and these little cross concrete beams. This leg with these concrete beams is part of the fish ladder, and it comes down here and it makes a turn. And that's also part of the fish ladder, and it comes down right before the asphalt underneath that concrete, and it makes another turn, and that's where the entrance is, which is a little backwards. We call this the entrance to the fish ladder, even though the water is exiting. It's because the fish enter in at this side. And in between these two turns is some grading, and you can see some little specks there. Those are actually butterfly valves, and this is what we call our attraction water supply pool. And so the attraction water supply actually ends up opening up into atmosphere. So it's not under pressure, it's not below tailwater, it's not encased in some kind of container. It's a pool, and we'll be able to walk over the top of it when you guys are here. But I don't think that's clear from the drawings that the attraction water supply, the intake is over here underwater. It comes down underneath the fish ladder, and it bubbles up into this attraction water supply pool is what we call it. Sam, you had a quick question?
Yeah. Can you point out monolith 9 and 10 on this picture? Is that something we can see here?
Yes. I'll get there real quick. And I think it's actually pretty sure this is 8, 9 is here, and 10 is here. If I remember correctly, but I'll check the drawings here in a sec. But I'm pretty sure it's like 9A, 9B, 10A, 10B, and this is 8A, 8B.
Okay, thank you.
Yeah, no, great question. So what you're not seeing is right here where that truck is if you were able to look over the edge, over the handrail, and look straight down at what we call the Wanapum Reservoir, which is this big body of water here, and you were able to look through the water, you would see the intake for the attraction water supply. So it is below water level. And it swoops down and curves and enters into the what we call the valve pit room, goes through the butterfly valves, which we can see and we have access to. It enters back into concrete, and it turns from a round 72-inch pipe into a 10-foot by 10-foot square channel. It goes, I think, about 80 feet, if I remember correctly. And then there's these concrete turning vanes to help guide that water around the corner. And it shoots 90 degrees to the right before it hits more stay vanes where it pops it straight up, and then it hits another elbow where it pops it out into the attraction water supply. And we'll go over that one more time, but all of that happens underneath this fish ladder. And so if you were to try to get to the valve pit room, there is an access hatch, I think right here, but the valve pit room is right here. So there's layers and layers of fish ladder and concrete that go down that are in between you and that valve pit room. And so the way to access that is, let me back up just a little bit. I'm going to use the orthogonal view. If anybody struggles with orthogonal, I can also change. So just let me know. So that truck was parked about here. This is that attraction water pool I was talking about, and the fish ladder turns aren't showing, but they're about right here. They're on either side of this pool. And so you can see where the water comes in from the intake. It's a 72-inch pipe. It curves down and does a 90 degree. So it does quite the turn. It enters in to this valve pit room, exits out, becomes that square channel. It takes that 90 degree, this 90 degree up, and then this 90 degree out. So all of this is concrete except for these square, and we call these galleries, and this is called the access hatch, the attraction water supply piping, and that's it. Everything, this is embedded in concrete. Not shown is the fish ladder. So there is fish ladder structure on about in this area. So there are some voids, which if anybody wants to look at going through that, we can certainly dive into the drawings and take a look. Libby, you had a question?
Does the butterfly valve automatically, do they adjust? And like what angle, or what are the parameters to why they adjust?
So butterfly valves, let me get to that real quick. Let me finish this and we'll jump to the butterfly valves real quick. So one last look. We operate at a normal max pool level of 571.5. You're going to see elevations on all of our drawings. You can always see what the change in elevation is, and that'll get you feet by just subtracting. So normal pool level is 571. Minimum tail level is 481. So that's our max and our min. The intake for the AWS, I believe I put that in Slack, so I hope you guys all have access. I don't remember that off the top of my head. And again, it swoops down and it goes through this elaborate to get into the attraction water supply pool. And here you can see from the top of the dam, where that truck was, to go down to the valve chamber. So you're going through monolith 6, and there's some voids there that go straight down. The butterfly valves are, they can go from anywhere from a 0 position, which is closed, to 100%, which is flat. And we do it by percentages. So it's either 10% open or 50% open or 90% open. And it sits there and it's on a control system. So there's an equation working in the background that automates that. And the parameters for automating it, or that it adheres to, is down here. And this is a little different than the O&M manual. So when it comes into this pool, it actually diffuses into the ladder to maintain a certain level. And what we're looking for is 1.5 feet over tailwater. So right here at the bottom of the fish ladder, there's this restriction to the flow, and we call it a slotted entrance. And the water level is supposed to be 1 foot. Sorry, I'm sorry. It's not 1.5. No, it's 1.5 feet. 1.5 feet over the elevation of the tailwater. And that's what the attraction water supplies. So the flow coming through the butterfly valves comes into the pool. The pool disperses that water into this arm and this arm of the fish ladder in order to provide enough water that this level of the entrance is 1.5 feet above tailwater. And it's all done automatically. So it does, it sits there, and we have a program. I can send you a map of it sitting there and fluctuating, or a graph of the percentages. But that's all done in the background in order to maintain that 1.5 foot over tailwater at the entrance of the fish ladder. So the main thing, and Skylar is much better at this than I am, so I'm stealing his line, is that what the butterfly valves are doing is essentially dispersing energy. So we can't have turbulent flow at the pool. It's got to be this nice laminar flow. And what they're doing is taking up some of that energy. And so they're restricting the flow, they're dispersing some of that energy, which is part of the reason we have cavitation there. So anything you're doing has to provide enough CFS, typical CFS, which I believe is noted in the O&M manual. There are CFS requirements for the AWS channel. So those have to be met. But can't come out and like geyser water out of the pool. Pauline, you asked for a graph of percentages for the butterfly valve opening. For how long of a period do you want? Because if we go, it's changing constantly. So I can give you a day, I can give you a week, or I can give you a year, or about 9 months, 6 months, 9 months, 6 months, 6 months, because we operate it 6 to 9 months out of the year. But you're going to lose some granularity with the more you go.
Can I ask for all of the above?
I will tell you, without the other data points, I'm not sure how much it's going to help you. I can certainly give it to you, but without other data points, it's just going to be a graph of that valve sitting there at percentages, at its different percentages. And I don't know if I can correlate that back to a change in CFS, because I don't think we monitor that. You might be able to calculate it. I don't have a calculation for butterfly valve on a 72-inch pipe, how much CFS based on percentage of open.
Through our control system, you can back calculate. I've got a couple photos that I'll show during training, or if we go off base, I can pull up my fish ladder training slide deck to give you all a little outline on that as well. But we do measure how much water is heading out through the fish ladder entrance. The water goes out, the fish come in. And that's a straight effect of how submerged. It's a big slot. We call it the slotted entrance weir. And so the amount of water, the depth that weir is submerged, and how much differential we have across the slot, you can throw those two into our spreadsheet, and it'll tell us how many cubic feet per second CFS of water we're flowing through that entrance.
Through the entrance though, but not through the AWS.
Yeah, the AWS system will be providing 70 less cubic feet per second than what we're flowing through the entrance weir. And I can run through that in my training real quick if we want.
And yeah, with that, you guys have access to me through Slack. You're more than welcome to email, stop in for a quick Teams. We can set that up. But we have Skylar here, so I'm actually gonna jump to him because he has a wonderful amount to say, and I'm hoping you guys have some great questions for him on his presentation. But then he can also help some of the questions that start to percolate about this. So thanks for being here, Skylar.
Oh, you're welcome. My pleasure. I enjoy this. It's fun for me, and I just get to be a big nerd. And so hopefully you guys get to enjoy, or hopefully you're able to appreciate me being a nerd. So I'll fire off. We'll start with Hydro 101 to get a little bit of a background on what Grant PUD is, where we're at, and kind of what we do. And I'm a terrible multitasker, but we'll get this going here shortly on the screen share.
While Skylar's pulling that up, I just want to say your guys' questions, please don't hesitate to ask, because they are really exciting me for the fact that you guys are giving this some actual thought. And so I don't care what the question is. I am absolutely thrilled that you guys are asking these questions, and so many of them are brilliant and wonderful, and I'm nerding out myself. So thank you guys. I really appreciate it.
You can also send your questions to me, but most of the questions that have come up, I'm just going to send straight to Shannon. just FYI. I will help facilitate.
All right, so this is the slide deck that Shannon and her manager put together, Jason, and I shoveled some stuff around. But this is a Hydro 101. This is a Shawtawanpum Dam, and you're looking here at the downstream side. A couple notes just as we drop into this. I'll get my laser pointer out here. This is the fish ladder entrance for the left bank fish ladder. And you can see a little riffle there. That's water heading out to attract fish into the ladder. We've got a lot of water running through the river right here. And this is one of the things we'll talk about maybe if I have time on the fish ladder. The design of the fish ladder has to account for the fluctuation in the tailwater. The river, as we pass more water through it, gets deeper and deeper in this area. And so that's one of the things. That's why we have to change how much water flows through the butterfly valves and the attraction water supply system, is because the tailwater elevation changes. This is our fish bypass. You can see this is where the fish go downstream. The juveniles, the small fish, head downstream, and we push water past the dam. We call it our fish slide in a comical sense. And then takeoff structure, this is where the power heads out in electrical form. The power heads through in hydraulic form, and we'll talk about all that. Grant PUD, established in 1938, headquartered in Ephrata. You guys will get to enjoy Ephrata, Washington, and your visit there. We own and operate 2 dams, Wanapum and Priest Rapids. They're both part of the Priest Rapids project, which is, we're federally licensed by the Federal Energy Regulatory Commission to operate these 2 dams. The original drawing when people were sitting around going, how do we control floods on the Columbia River, was actually to put one dam in. And Harza sharpened their pencils and said, hey, we can actually make use of all of the elevation the river loses through the Priest Rapids area by putting two dams in. It'll be more valuable than putting in one dam. So, you know, it's funny, in the utility space, we're vertically integrated, they say. So we generate power and we deliver it all the way to customers and to use. You know, I do joke, it really pays to bill everybody in the county. We have a pretty good resource, and you know, the money is going to come in. People pay their utility bills. So it's an interesting industry because all of our design scopes are 40 to 50 years. You know, everything around lasts a long time. Even wood poles out in the desert, you know, we see 70 years of life out of a telephone pole or a utility pole. Sorry. But this is Grant PUD. As you can see, next slide, you know, Washington State, right in the center is Grant County, or center east. Ephrata's out here off the edge, where these two highways meet. Wanapum Dam, where our project is here, and then Priest Rapids is downstream. A couple interesting notes on this is the Wanapum pool is all the way from here to here. The river doesn't fall a whole lot. And then the Priest Rapids pool is only from here to here. And it's like the pool length is a quarter to a third the length. But the reason it's called Priest Rapids is because the river used to hustle right through this section. We lose the 70 feet of elevation between these two dams is the same 70 feet that we lose from here to here. So before we impounded the river, you know, this was the Priest Rapids. The Wanapum people was a band of Indians that lived along the river, and they were the religious group, and so they were known as the priests. And they lived along the rapids, and that's where the origin of the Priest Rapids came from. So you can see Ellensburg, you know, Yakima. I did want to pop up just a real quick. You know, this Washington State, you can certainly see as you zoom in, you know, we're in the arid area. This is Priest Rapids, this is Wanapum, and Yakima Training Center. We get to hear the booms of the bombs occasionally when we're at work at Priest Rapids. But there's the two locations. It is funny, the first bid item for Priest Rapids Dam, Priest was built before Wanapum, or they started construction of Priest Rapids first. First line item was to build a road to the project site. There wasn't even a road to this area that was capable of handling the traffic that needed to come to Priest Rapids to build the dams. So I wanted to high level discussion. This is 101, and I get into the weeds really quickly, so sorry. But I think, you know, the broad range of folks we have here, from electricals to mechanicals to renewable energy and welders, fabricators, I think it's good to step back and think a little bit just about power, you know, and what power is. I grew up with engines and cars, so, you know, I knew horsepower, and that's torque times RPM equals power, right? In the river, the power is the differential, how much difference we have across the dam, which we call head, right? At Wanapum, we're going to be around 75 feet, right? The upper pool is 75 feet above the lower pool, and that's potential, right? We go back to our middle school physics, and that's potential energy, right? We've got a difference, and the dam's doing a whole lot of work to hold that potential back. And then we've got the flow of the river, and the potential times the flow equals power. Just like with a car, torque times the spin, the RPMs equals power. the head and the flow equal power. And then we do, we convert that head and flow using a turbine into rotational power. And then we go up into our generator and make that rotation energy. We start rotating a magnetic field, and that then gets coupled to static coils that have fields collapse. The magnets go past it, and we generate an electric current, right? And Chris probably can explain that more eloquently than me, the mechanical engineer. But we've taken all of the flow of the river and suddenly turned it into just a washing machine, a wash of electrons moving back and forth on these lines. And what we do is then we generate at Wanapum, it's fun, 13,800 volts is what our generator bus is at. And then we take it out to a transformer and we make another magnetic field that collapses on top of another magnetic field and take it up to 230,000 volts, right? And we run 230,000 out across the county. We've got huge potential, 230,000 volts, and low flow, low current. Flow is hard to move, right? You think about trying to push air through a tiny stir straw, right? You can't move much air through a stir straw, but you can, if you grabbed a 2-inch PVC pipe and blew through it, no problem. And so that's why we change potentials with electricity, is to have the most economical amount of flow, right? So it's an interesting thing for me to think about all the different ways we play with flow and potential as a form of power. And so we see that in this hydro system. That's the foundation of what we're doing, right? Is we're taking flow and potential and converting it from one means to another, and then changing the potential to move it. The grid, and I've got a slide further on, right? Our generator is connected to motors and generating plants in northern Baja California, in Canada, in Colorado. The whole Western US is all on one grid, and all of those electrons are sloshing back and forth with each other. And they don't, if we tried to make our generator go a different speed, it's not going to go a different speed, because it'd have to make Grand Coulee speed up and every other generator and motor that's on the system that's synchronized to that slosh. It would have to overcome that. Does anybody have any questions on this kind of fun little graphic? And then, yeah, we do step it down to a safer voltage. One of the revelations I had recently, and this is an aside, but welcome to learning time with Sky, is the cost of insulation really is what determines what voltage we move all of this stuff around at, right? Because we could more efficiently generate if we went a higher voltage on our generator, but we'd have to have huge amounts of insulation there, right? Air's a decent insulator. And when we put an overhead transmission line up, we can go to 500,000 volts because all we have to do is spread the things apart. And so the insulation is cheap because we're air. As soon as insulation gets fancy and has to resist all of the heat that we put in a generator and all of that, then we're going to go to a lower voltage and take some flow losses because we don't want to pay, or we can't, we're just don't have a way to insulate 500,000 volts, in the size of my cubicle here. Right? Libby?
Do all these systems and other systems talked about in the problem statement, do they go through like a yearly inspection, or how is it that you catch problems that arise?
Yeah, we inspect annually on the fish ladders. Actually, at Wanapum now, we're hoping to go to every other year based on resources, and it takes a lot of work to to get all the water out of that space, the spaces that we work in. And it's a lot of the work that we do when we do fish ladder maintenance is mucking mud, dirt out of the way, because the river carries sediment, and we try, one of the things we have to do to make fish want to move through our fish ladders is, you slow that water down. When you slow water down, the sediment drops out of it. And so we do a lot of cleaning where we're just out scooping mud out of galleries and the like. So and as you might have seen, a lot of these galleries are so small, it's not like you can, oh, we're just going to lower a front end loader down there. I mean, it's a lot of times the only tool you get to use is a shovel and a wheelbarrow. So we understood how we convert flow and energy, or flow and potential, into power. These are some photos of building the dam. At Wanapum, it's neat. They built the whole thing in the dry off to the side of the river. And then at the very end, they closed up where the river was moving and routed the river through the powerhouse. So pretty fun photos. We'll travel on because I'm going to burn through all my time. Another interesting, just for the mechanical group or for people to kind of get their head around, maybe familiarization for some of the electricals in the room. 3 different kinds of turbines in the hydro space. The Pelton turbine over here uses very high potential and low flow. And if we look at the way, from a hydraulic engineer standpoint, we are changing the direction of flow like 180 degrees in a perfect Pelton turbine. We don't use a whole lot of water, but it is a jet. It's hundreds and hundreds of feet ahead. A Francis turbine ends up being kind of mixed. You're changing direction, not changing 180 degrees, but you're changing 90. And so that's a mix. You've got higher flow, but you also still have pretty decent amount of head, higher potential. And then the Kaplan, which is what we have at Priest Rapids and Wanapum, is more of an axial flow unit. We've got a lot of flow. It's the Columbia River. We talk in 1,000 cubic feet per second anytime we're talking about what the river flows in the Columbia. And, it averages 150 to 180,000 cubic feet per second. So you take that number and multiply it by 7.5 to get to gallons per second, or 1,000 gallons per second. And you start, it's just a staggering amount of water. So we have tons of water, not a whole lot of differential in the realm of hydro. So we have it's an axial flow, it's a Kaplan unit. And we can actually adjust the angle of all of the propeller blades here to suit the best efficiency point for the machine. So there's the 3 types. Both the vanes and the buckets are fixed on these. The Kaplan, you're able to adjust.
Skylar, by chance, did you mention that Grand Coulee higher up on the river uses the Francis?
I did not. That's it. Yeah. Cooley's Francis. Cooley has higher head. Bill, I'm not sure what the head is off the top of my head. But Grand Coulee's much more head, but they still got the Columbia, and we don't have very large tributaries in between Grand Coulee and Wanapum. So the flow is about the same, but higher head. So the way the water travels through, you extract more energy by changing the water's direction. That's the kind of fun way to think about it, is how do we best extract the energy that's available, or the power that's available. Another shot of a drawing, we connect the turbine and the generator. Most of the big units are all vertical units.
Skylar,
Here's,
Alvaro
go.
had a question.
Oh, sorry. I'm working 3 screens here.
Hey, Skylar. I did a tour at Rock Island, and they had a fourth one. It was like a enclosed, like a submarine device. It looked kind of cool. Is
Yeah,
that something
they
that's
have
very
a
specific?
bulb unit, and I've got a drawing of that a little bit further on that Shannon put in. Ours isn't exactly like that, but their bulb unit is still, it's a Kaplan turbine, but it's a horizontal unit, and the generator is actually upstream, hidden in the water passage or hidden from the water, and upstream. Our Kaplan units that are horizontal are the generators downstream, and they're smaller. The water path is called an S turbine at that point. But some of Rock Islands are bulb turbines where the generator is upstream of the turbine and sitting in the water passage. Another shot of Wanapum. This is as we talk, we'll talk right bank or left bank, right? For orientation, that's always when we're standing in the river looking downstream. What's on the right is the right bank, left is the left bank. So if you're looking upstream, it's backwards. Here's our right bank, here's our left bank. This is where the river was closed. And if we look in the satellite view, oh, GM Forum's coming up. Are we that close? We are. Okay. The river actually used to just run right along here. And you can see where they built the whole dam in the dry. And then at the very end, they closed this section off and routed the river through the dam. Here's a cross section. Again, this shows some of the work. The water moves through the turbine. Got a bunch of cranes, where the mechanicals around here get into crane nerdom. This crane can pick 700 tons when we have all of our hooks matched together working. So multiply that by 2,000 to get how many pounds we're picking at a time. Couple shots of the turbine. You can there's a bucket in the photo for scale. Almost 30 feet across is the Wanapum turbine. Here's more scale of the machine that we're dealing with. The generator is not in place, it's above, but you can see some of our mechanics that are starting to bolt together the top of the turbine shaft at Wanapum. Walkway. This is all the structure that regulates the flow through the unit. More photos. This is the stator, the outer portion of the generator getting lowered in, and that's stationary, but that's what has all of the coils that get the magnetic field passed through it to generate. And this is good for about 120 megawatts is how much that coil's ready for. Here's the photo of the S turbine that we have at one of our smaller plants mounted on a ditch irrigation canal. We affectionately call them the ditch plants. This is for the electrical folks. Here's our generator step-up transformer where we move from 13,000 to 230,000 volts to tie in with the grid that's here in the Northwest. The reds are all 230. Yeah, the blue is, oh no, the reds, sorry, are 500, right? Chris, I believe, are 500 kilovolts. The blue is a DC line, I believe. That's a 500 kV DC. So there's only one conductor and the rest of it's headed through ground. Kind of wild to think about, right? And then a bunch of 230. Here's the spillway in action. Our spillways are designed to be able to pass the whole flow of the river, even with the powerhouse offline. up to our design capacities are right at 1.4 million cubic feet per second of water. We'll get a little bit further. The flood that initiated building dams on the Columbia, or the palatability of it, was around 600,000 cubic feet per second. Oh, that's my next slide. Perfect. 633,000 cubic feet per second is what flooded the Portland area. Vanport was the town that was the most devastated, and 18,000 was the quantity of people, or the community. 18,000 inhabitants lost their homes due to flooding in the Columbia. And so the US government got together with Army Corps of Engineers and said, how do we stop this from happening? And they started the plan that started putting things in place. And based on a sketch on a map, Grant PUD said, hey, we want to build one of those dams, and went through the courts and did everything necessary to be able to build the 2 dams that we have today. Spillway gates, we won't go too deep into this, but this is how we manage flow through the spillways, by either opening underneath, opening above, or opening a standard flat gate. A little background on, I'm going to go ahead for a second, then we'll go back. Hydropower, these are the people that we just employ inside our power production area at Grant County PUD. From archaeologists, we've got Indiana Jones working for us, all the way, permitting, public affairs, risk. We've got a data scientist on my team who's just starting to look at machine learning and AI. How do we look at the mountains of data that we have to make good, educated decisions? So onto the fish ladder. This photo, we've got the tail of a fish. The fish ladder, I hope it makes a little bit of sense. It's a ladder for adult fish that are heading up to their spawning grounds to return to where they were born, to lay eggs, fertilize them, and then most of the salmon die after that. So this is their final trip. We make out of concrete a series of 1 foot or of pools. Each of these pools is 1 foot higher than the next one, and that allows them to jump. This design is set up so that there's calm water right in the center here that they can rest after a jump. There's also holes in the walls that they can dive through. Each of the walls here is 6 feet high, and the amount of water flowing down this that you see right now is 70 cubic feet per second. What we do when we operate the ladder, and this sketch is an eye chart in some ways, but this is my nerdy bread and butter here. And this is Priest Rapids, but it's a great photo that we have here, and the principles are the same. This is the entrance for Priest Rapids, and at this high of a tailwater, there's a lot of water in the river right now in this photo. So this entrance is probably passing around 1,100 cubic feet per second of water. The fish ladder here, Priest is designed a little bit differently, is passing 90 cubic feet per second. So I need to have 1,100 coming out here, and I only have 90 flowing down the river. So at the bottom end of the ladder, I have to insert 1,010 cubic feet per second of water, right? Multiply that by 7.5 to get gallons per second. We got a lot of water to put in here, and it all needs to be quiet and calm so that we don't distract the fish from finding the waterfalls and swimming up them. And so that's the challenge of the attraction water supply system, is to somehow put 1,000 to 1,100 cubic feet per second of water into a pool as calmly as possible and as efficiently as possible. So that's the problem that we solved at Priest Rapids to make an independent supply. Priest was unique. It actually has all the way across the dam. It's got a conduit that's 10 foot square underneath all the concrete, in the concrete, that carries water from the left bank fish ladder to the right bank. One of them didn't have that. It's got a fully independent system on the right bank. They wanted redundancy at Priest Rapids when we relicensed the dams. And so that was the first project I had at the district, was to somehow build a redundant water supply for the left bank fish ladder at Priest Rapids. So we're 5 minutes. Is it how am I doing on time? Did we go to the top of the hour or the bottom? Or am I past already?
About 6 minutes.
What's that? 6 minutes?
Yeah, you're good.
Super. All right. So let me open up my other slide deck that will give you just a little bit more background on this. My fish ladder training slide deck.
And we can always provide both of these in the Slack channel. So I can push these presentations into Slack. I also, for those of you, some of you have responded on Slack, but I did get some percentages graphs up in Slack. So you have an 8-hour last week and since May. I also provided headwater, tailwater, and a couple other elevations. So we've got those.
So I'm just going to grab, there's no continuity in these slides, but I'm just grabbing out of this is a 4-hour slide deck for fish ladder training that I give our mechanics and operators. Well, I've had mechanics fall asleep. My operators didn't fall asleep. Some mechanics in the back, I think, fell asleep. Shannon, I'm not sure if you can confirm or deny. She was in the room. I was doing it like this. But from the operations and maintenance manual that Shannon referenced, we changed in the mid-90s to a slotted entrance instead of a weir that followed tailwater. So the original design concept was, okay, we'll have a weir that follows tailwater, and then you just have a fixed amount of water that you need all the time. It doesn't matter how much water's in the river. The weir is on controls and it follows the tailwater. So there's only, I'm just making a number up, 50 square foot slug of water that we're pushing into the tailwater. Now, this is placed and it's static. This weir, it's called a sutro weir, sits in there. And so as the tailwater comes up, you can see there's more exposed area. And the fisheries agencies want to see 1.5 foot of differential. So one side of this weir is the water level is 1.5 foot higher than the other. And that generates a punch out into the tailwater that attracts fish into the fish ladder. They're swimming upstream looking for where to go. They may see turbine discharge. They probably don't really want to dive and go up the bottom end of a turbine, right? It's just way too spooky. Doesn't look like anything that they know natively, right? But this looks closer to a riffle in a stream or a waterfall that they'd be used to jumping up. And so they are attracted to this, and we put a current into the water to attract them into that. So that's the depth. I've got a great cross-section view that helps me, and hopefully we'll get there, get my head around what actually happens in the bottom end of the fish ladder, right? Talk about the tailwater changes elevation, right? Because we, as a hydro plant, if there isn't money to be made and we have the room to store water, we're going to shut the river flow way down until we can make money and run our generators. And so there may be times at Priest Rapids, my minimum flow is only 36,000 cubic feet per second. So the tailwater may go way low. Our fish ladder still needs to work, And so that's why this is a sectional view that I've got. Oh, okay, you can see my mouse cursor, right? I don't have my pointer right now.
Yeah, we can see it.
Yep.
All these weirs, these are the 6-foot tall walls that we have. As the tailwater comes up, more and more of these weirs get submerged, right? I'm looking at these in an elevation view, this section AA. They get submerged, and we've got all kinds of means inside the fish ladder through the attraction water system to feed water in through these. Actually, they're shown right here. This is the gallery that connects to the attraction water supply pool, and it feeds water in. So if I end up with water that's to the depth of all the way up here, I feed water in through a series of weirs into this lower section, because I still have to keep fish swimming up this. Fish are always looking to head upstream, right? And so the attraction water system throws a bunch of water into the bottom end of the ladder to always have 1 to 2 feet per second of water flow in this way. It's really easy up higher because I've just got 1 foot waterfalls, right? But over here, I may have a weir that's submerged 10 feet. So I've got a 14-foot wide by 10-foot deep. I still need to maintain 1 to 3 feet per second of water through that, right? So I need a whole lot more water to generate that velocity. So that's what the AWS pool does. I saw another hand raised.
I actually threw in the chat because we're at time.
Okay, sorry.
So
this is welcome to the Art of the Sky.
No, you're good. You're good. I think it was really informational, and I just let the students know, since we don't have a lot of time for Q&A, to email questions to you, and also, of course, put them in the Slack channel, and we'll respond to them as quickly as we can. So hopefully today was helpful. And Skylar, thank you so much. And I'm sorry that we had to cut you off.
Yeah, thank you.
Yeah, sorry that
we just
it's hard to condense.
No,
you might imagine.
It's a lot of information. And so if there's anything else you think that's pertinent that you didn't get to cover today, feel free to email that out as well. I'm sure the students would be happy to receive more information.
Will do.
So I appreciate everybody jumping on today, and hopefully it was helpful. Again, if you have any questions, just send them our way. Otherwise, we will see you on August 16th. You have to be there on the 16th in order to be ready and bright and bushy-tailed on the 17th. Did I get I totally did the dates wrong. It's on the 14th. Sorry. That was my last thing, Took. They're all running together. Be there on the 14th. All right.
Thank you.
Y'all have a great day. Take care.
Thank you.
Thank you.
Bye, everyone.
Thank you, everyone.
Looking forward to seeing you all.